So next, let's talk about quantitative data. So the distribution of a quantitative variable tells us a lot about what values the variable takes on and how often it takes on those values. And also we want to look at the shape that this distribution takes on. So two main ways to do that would be histograms and stem plots. Histograms show the distribution of a quantitative variable by using bars where the height of each bar represents the number of individuals who take on a value within a particular class. And it's important to note that unlike bar charts, these bars touch. These bars touch. The next version is going to be stem plots. Stem plots separate each observation into a stem and a leaf that are then plotted to display the distribution while maintaining the original values of the variable. And I'll go into this a little bit more, but let's say I have a cat who's 9, 11, 13, and 17. So if I wanted to arrange this data in a stem plot, I only have one cat. She's 11. I'm sure you'll hear her at some point. I would make my stem the 10s and my plot the 1s. So I could have 0 for this 09. Then I could have 1, which would give me 1, 3, 7. And we don't separate them with commas. So this is your most basic stem plot. But first, let's talk about histograms. So histograms are appropriate for quantitative variables, right? Not categorical. We want quantitative variables. And they can take on many values. And these are really great for large data sets to kind of summarize things down. What we want to do is we want to divide our values into classes, groups, bars, bins is another word for it. You might see in the data in the text. So our bars have equal width, right? So if we were making ages of bins, we'd want to do like 30 to 34, 35 to 39, right? Those all are equal bin width. Next, what we need to do is count how many observations fall into each of those intervals or bin categories. We can then change those to percents by dividing by the total number of observations. It's totally up to you. We would then want to draw our histogram representing the distribution where the bar heights are equivalent to the number or percent of observations in each interval. So let me go ahead and show you guys an example. So here we have the freshman graduation rate. So this rate of people who start as freshmen who graduate after 4 years of high school from 2016 to 2017, right? So we have one state that had a graduation rate between 70 to 72%, right? We have 14 states that had a freshman graduation rate of 87.5 to 90%. And here's our graph. We can kind of see the distribution. This appears to be left skewed, which I'm actually like 2 slides ahead of myself, but this would be a great example of a histogram. And you can see that each of these bins have a width of 2.5%, making them equivalent and even. So when we examine a histogram, we want to look for our overall pattern or even any striking deviations from that pattern. By deviations, we mean outliers, we might mean changes. Outliers are data values that are really far away. If you're looking at income in the United States, outliers would be like Jeff Bezos, Elon Musk, right? They're way, way outliers. And we can describe our pattern by its shape, where its center is, how much variability is going on. You'll sometimes see variability referred to as like your spread of your data or your range. And it's an important kind of variability. It's important to look at the variability of our data. An important kind of deviation is an outlier. So that's something that falls outside the overall pattern. Like I said, if we were looking at income, that'd be the Elon Musks of the world. That'd be the Jeff Bezoses as well. So when I'm looking at my shape of distributions, I'm looking at symmetric and skewed distributions. So a distribution is symmetric if the right and left sides are approximately mirror images of each other. A distribution is skewed to the right or right skewed. That means the hump's on the left, right? It's a little opposite. If the right side of the graph is much longer than the left side, right? Like it's, if I was to draw where like maybe the middle was, it's kind of skewed. This side is longer. This opposite is true for left skewed. Left skewed has a hump on the right. And we'll talk more about skewness as we go into talking about symmetric, normal, distribution, bell curve, right? These will all come up in chapter 3.